Greetings, statistics scholars, and welcome to the first video of our coverage of chapter number 5. In chapter number 5, we're going to start to take a look at how we can use, you might call some classical or traditional techniques to perform hypothesis tests and build confidence intervals. We're going to be doing the things that we learned about in chapter number 4 in new and different ways, but actually ways that actually predate the methods that we learned about in chapter number 4. The first example that we're going to take a look at today is a problem from your textbook, exercise number 10 in section 5, that deals with standardized z-test statistics. Suppose that we were given a hypothesis test, and the hypothesis test was that perhaps mu, the population mean, is equal to 10. That's the null hypothesis. But somebody's seeking evidence to see if mu is not 10. Is there statistically significant evidence that the population mean is different from 10? They've got these two competing hypotheses that they're going to test. And so they take some data. They take a sample of size 75. And from their sample of size 75, they find a sample mean of 11.3 with a sample standard deviation of 0.85, and it turns out a standard error of 0.10. Remember that standard error is the standard deviation of the x bar. The s is the standard deviation of the variable x itself. The standard error is the standard deviation of our statistic x bar. Now, what they want us to do in this problem, the goal of problem 10 is to compute what we call the standardized z-test statistic for this particular scenario. To do that, we're going to use the equation that you see here. Z is equal to the sample statistic minus the null parameter divided by the standard error. This is derived from our idea back from earlier in our learning that said a z-score is a data value minus a mean divided by a standard deviation. But here we're talking about the statistic of x bar. The standard error is the standard deviation of the x bar statistic. And if the null hypothesis is true, the mean of the x bar statistic should be 10, the value that we call the null parameter. So by subtracting the null parameter from our sample statistic and dividing by the standard error, we're really taking our data value minus the mean of our sample statistics and dividing it by the standard deviation of the sample statistics. What would that turn out to be here? Well, we can use the values in the problem. Our sample statistic was x bar equal to 11.3. The null parameter is the value of the population mean according to the null hypothesis, which is 10. So in our numerator, we'll have 11.3 minus 10, which is 1.3. Now, to get our z standardized statistic, what we're going to do is we're going to divide that result by 0.1, which is our standard error in the problem. 1.3 divided by 0.1 is going to give us a standardized z statistic of 13. So that is the answer to this problem. And that's how we find z statistics, is by means of this equation here that says take your sample statistic, subtract the null parameter, and divide by the standard error. So let's practice with that again, and now let's use it to actually do a hypothesis test. Let's use standardized z-scores to help find p-values and conclude a hypothesis test. What we're going to see here is that those standardized z-statistics give us another way to find a p-value. Suppose we're doing the hypothesis test that's testing the idea that the population mean is 2.5 versus the alternative hypothesis that mu is larger than 2.5. So we have a we have a right-tailed test here, not two-tailed. We have a right-tailed test. And as we're doing it, based off of the data that we take, the sample data we take, we find that we have a sample mean of 4, certainly bigger than 2.5, and a standard error of 0.8. Using that information, we're going to find the p-value for this test and draw a conclusion about our hypothesis. But we're going to do this in 2 different ways. The first way of doing it is by going to a normal distribution that is based off of the original ideas. The null hypothesis says that the mean is 2.5. So if the null hypothesis is true, that's the mean of the sample means. And we're also told that the standard deviation of the sample means is 0.8. So one way to find the p-value for this test is we can go to StatKey and we can create a normal distribution that has those parameters. So we see here our normal curve. This one right here is the standard normal curve, mean of 0 and standard deviation of 1. I'm going to change the parameters. I'm going to change this so that we have a mean of 2.5 and a standard deviation of 0.8. Why? Because those are the values from the problem. In the problem, the null hypothesis hypothesized that mu was 2.5, and that would therefore be the mean of the sample means. And also we were told to use a standard error of 0.8. So I'm going to redraw the normal curve so that the mean, the center, is above 2.5 and a standard deviation of 0.8. Now let's look for a p-value. Remember, this is a right-tailed test. So I'm going to click on right tail. And then I'm going to change my cutoff value here on the bottom to be the number 4. Because remember, that was our x bar. Our x bar was 4. So if the null hypothesis is true, then we would have a normal curve centered over 2.5 with a standard error of 0.8. And we can look and see what StatKey has told us. StatKey tells us that the area to the right of x bar equal to 4 is 0.03. And remember, our p-value represents the proportion of statistics that would be more extreme or more unusual than ours. In this case, that means to the right of x bar equal to 4. StatKey reports that that area to the right of x bar equal to 4 is a probability of 0.03. So here we found our p-value, and we certainly have one way of finishing the problem now. If I go back to my question, we've just found the area to the right of x bar equal to 4 using the normal distribution that had a mean of 2.5 and a standard error of 0.8. We found that to be 0.03. What would the result of the test be? Well, if we're doing this at the 0.05 level of significance, that's certainly going to lead us to reject our null hypothesis. 3% is less than 5%. So since p is less than alpha, we'd reject the null hypothesis and conclude that we think that there is sufficient evidence that the mean, the population mean, is larger than 2.5. Now that's one way of doing the problem. But now let's take a look at how we can use the standardized Z-score to reach the same conclusion and find the same p-value. So remember, our definition of Z-score says that to find a Z-score, you should take your statistic subtract the null parameter, and divide by the standard error. That's what we did earlier in problem number 10. What would that give us here? Well, our statistic here was 4, and the value of the null parameter was 2.5. So in the numerator, I have 4 minus 2.5, which is 1.5. That needs to be divided, though, by the standard error, with the standard deviation of the sample mean. Since that was 0.8, my z-score, my z-test statistic, will be 1.5 divided by 0.8, which ends up being 1.875. So here in this problem, given the null parameter, given the statistic, given the standard error, we have a standardized z-score of 1.875. Now we can use that z-score. The cool thing is we can use that z-score to come up with the same p-value that we saw earlier. What I'm going to do now is, instead of using a normal distribution with a mean of 2.5 and a standard deviation of 0.8, I'm going to just use the standard normal distribution. Let's go back to our StatKey. I'm going to reset the plot. StatKey always begins by assuming a standard normal distribution, that distribution that has a mean of 0 and a standard deviation of 1. So I'm just going to keep it with this setting. I'm going to indicate that we've got a right-tailed test. And now I'm going to go to the bottom, but instead of putting 4 for our cutoff, that was the appropriate cutoff if we had the other normal distribution with the mean of 2.5 and a standard deviation of 0.8. But now we've got the standard normal distribution. So we want to use our z-score as our cutoff value. That was 1.875. So I'm going to use 1.875, my z-score, as my cutoff value. And I'm going to read off the area that's associated with it. Here's our 1.875. And voila, we see that the area to the right of 1.875 using the standard normal curve is, again, 0.3. Exactly the same value that we had found before using the normal curve with a mean of 2.5 and a standard deviation of 0.8. But now we found it using the standard normal curve and the z-score. So we see here that we actually have two different ways of computing a p-value for a hypothesis test. One of the approaches for finding the p-value is to, well, use a normal curve whose mean is based off of the null parameter and that uses the given standard error. That's one way to do it. Another way to find the p-value is, instead of using that normal curve, we can just use the standard normal curve. But if we're going to use the standard normal curve, we have to use the standardized z-statistic. So we'll compute out the z-statistic from the values in the problem, and then use that z-statistic with our standard normal curve to find our p-value. Two different ways for finding the p-value, two different ways for helping to resolve the result of the hypothesis test. So I hope this has been instructive in the areas of finding standardized z-scores and how we can use them as an alternative way to help compute p-values for hypothesis tests. I wish you well, and stay tuned for more videos forthcoming on section 5.1.